In this video, I'm going to show you how you actually run the numbers and compute a correlation for yourself using the Pearson's R correlation coefficient. There's other types of correlations that you can run for different kinds of data, but the Pearson's R is definitely the most frequently used one and the most useful, but we're going to talk about how to compute it and when it is appropriate. This is a little bit more advanced than the other equations we've seen before, but all the same rules apply, where if you just keep your notation straight and you're careful with your order of operations, it's nothing outside of what you're capable of. So as mentioned in the previous video, correlation, when you're analyzing your correlational research, is about quantifying the strength of the relationship between your two variables. A strong relationship between your variables is going to be when your data points tend to fall closer to that best fitting straight line. The closer all of your data points cling to that best fit line, the closer you are to a perfect correlation. The more those data points are spread out and very diffused and create that more amorphous cloud-like shape, the weaker the correlation between your variables, because that would depict a relationship between variables that is farther from perfection, where the data points fall farther from that best fit line. So correlation is going to capture the strength as well as the direction of the association between your variables using a single numerical value. Some properties of your Pearson's are: one is that it's going to evaluate pairs of raw scores together. What this means is that you don't need to standardize your variables to be on the same scale whatsoever. You could correlate the association between GPA on a 0 to 4 scale with a variable like exam score on a scale of 0 to 100. Doesn't matter. Correlation sort of does a bit of standardization of the variables kind of underneath the hood of the equation, so that it doesn't matter if your variables are on completely different numerical scales, you can correlate them together. Another property or another feature of this property, when I say the Pearson's R evaluates pairs of raw scores, to do a correlation for each participant or each data point, you're going to need their value on variable X and their value on variable Y. So if any of you were wondering why I was harping so much when you were creating your projects on making sure that you distinctly defined your variables and did not have questions that asked about both variables simultaneously, this is why. You can't run a Pearson's R on a single value, as someone would provide when they were answering a question that asked about both variables at the same time. This is why you needed to have separate questions for variable X that were distinct from the questions about variable Y, because Pearson's R is about evaluating pairs of scores to figure out whether or not those scores are associated with one another. This point is very important for learning how to do your computation. The value of a Pearson's R is always in between the range of -1 and +1. There is no such thing as a correlation outside of this range. Part of what the equation for the Pearson's R accomplishes underneath the hood, again, is basically the variables will be standardized such that the relationship between the variables is going to be put in terms of the variance that they share together. And a perfectly negative relationship, essentially those would be variables that share 100% of the variance but are in the negative direction, versus variables that are perfectly correlated that share 100% of variance in the positive direction. That would be a Pearson's R that was a positive one. Variables that are not related at all, that gets you a Pearson's R of 0, meaning that the variables share no variance whatsoever. There's really no connection or association between two variables that have a Pearson's R of 0. So, since the R is about proportion of variance shared between variables, it would be impossible to be outside of this range. Again, the spectrum of correlations falls from perfectly negative to 0 to perfectly positive. So I'm going to say here right now, if you run your Pearson's R computation by hand and you get a value that's outside of the range of -1 to +1, you necessarily made a mistake. The equation takes care of that for you by necessarily turning your raw data into a value that will fall between this range. So I repeat, if you calculate your Pearson's R and it is outside of the bounds of -1 to +1, you inherently have made a math mistake. Okay, diatribe on that over. So given that Pearson's R's can fall between this range, obviously they can have a sign associated with them. So any Pearson's R that has a negative sign, when you compute it, that's a negative relationship between variables, whereas a positive Pearson's R tells you that there's a positive relationship between variables. Another important feature of interpreting your Pearson's R is about the strength of the relationship. So to evaluate the strength of the relationship, at that point you can discard or disregard the sign. You don't want to get rid of it, you just don't need to use it for interpreting the strength of the relationship. To interpret the strength of your Pearson's R, you just look at the absolute value of your obtained R. So a value of -0.6 would actually be a stronger correlation than an R that you computed that was a positive 0.4, because the stronger correlations are those that are further from 0. So again, in interpreting the strength of your R, you don't need to look at the sign. You don't get rid of the sign, because that tells you valuable information about the direction of the relationship. But make sure that when you interpret your R, you're not looking at the sign, you're just looking at the absolute value. There's a few assumptions that need to be met before you can reasonably use and interpret your Pearson's R. All of our inferential statistics that we'll be learning from here on out will have a few assumptions built into the analysis, basically things that you need to at least make sure are met or approximated to be true about your data before you can reasonably use this analysis. So one, as I mentioned before, your variables should be related in a linear fashion. If your variables are related in a nonlinear fashion, it's not that you won't be able to run your Pearson's R, you'll still be able to do it. It's just that your Pearson's R is not going to accurately capture the relationship between your variables. So to properly use a Pearson's R, you need to ensure that the variables are related in a linear fashion. Additionally, and this is another point that I kind of harp on a lot early in the semester and it becomes relevant now, both variables, when you're running your Pearson R, need to be quantitative. That means they need to either be on an interval or ratio scale of measurement. So whenever I was going on and on about how you can't put gender into a Pearson's R, right, because gender is just typically a question where people are placing themselves into a category, this does not work to go into a Pearson's R. Now, SPSS is going to let you run a Pearson's R with gender because the information written into SPSS will be a string of 1s and 2s. But the thing is that those 1s and 2s are just stand-ins for category membership. So you need to go beyond thinking, what am I capable of running in SPSS, to does this analysis even make sense? And if you're putting a variable that is not interval or ratio scale into a Pearson's R, that analysis will be uninterpretable. So you need to think, again, beyond what will I be able to run in SPSS to what analysis should I run? Okay? The general approach when you're computing your Pearson's R is again going to be pairing scores from your X variable with scores on the Y variable. So your data set's going to need to have all of your participants' scores from X paired with their own Y score, because you're going to see whether or not all of your participants' X and Y scores are kind of going together. To do this, the analysis is going to test whether or not those paired scores occupy the same relative position. Again, these two variables do not need to be on the same quantitative scale, because essentially what the equation is going to accomplish is sort of putting people into percentiles. So do people who score very, very high on the SAT also score very, very high on a math exam? This is what the correlation is going to enable you to do. So again, despite the fact that this equation looks a little bit more advanced than we've seen before, it's because it's able to do all this within a single analysis. So here's your formula. Like I said, we're going to break it down, and it's nothing you can't handle. There she blows. Okay? This is your equation for a Pearson's R, and you might be thinking, what the fuck, that's insane. Just take a pause and look at what you're seeing here, because literally nothing in here is something you're unfamiliar with. So I'm going to walk you through all of the pieces of this equation, and I'm going to explain. I'm going to show you an example where I walk through all the work to compute a Pearson's R, and then at the end of this lecture, there's a practice problem that you can do, and we'll have more practice problems coming up before the exam. So you'll have plenty of practice to do this, and I swear to you, it's not as bad as it looks. So let's break it down. First off, here's some really easy parts that you don't need to think too hard about. You see here in this parentheses sum of x, and in this parentheses sum of y, right? It's a sigma x. This means that I'm going to need to sum up all of the scores x. So for all of my participants' x scores, I'm just going to sum up that entire column. Since that's within a parentheses, I know that I need to do that summing before I do anything else. Likewise with summing up all of the scores y. For all of my participants' y scores that will be in their own separate column, I just sum up all the values in that column. N is just the sample size. That's pretty easy. We've got that sum of x down here as well, and sum of y here as well. So just by summing up all of the values in the column representing your variable x, you're going to get that and plug that in those two places. Same with your sum of y. Now, this piece and these pieces here are a little bit more confusing. I want to make sure that you know what exactly you need to do for these steps. As opposed to over here, there are two conflicting mathematical commands present within just this term where you see sum of x, y. What you need to make sure to do is to look at this piece and think to yourself, what comes first, multiplication or addition? It's multiplication. So since I'm seeing here sigma xy, what I'm being directed to do is multiply together the x and y score for every participant first, and then sum up all of the xy values. Okay? Do not, I repeat, do not multiply sum of x and sum of y together, because you will be way off. And as you know, you multiply before you add. So when you see this, stop and think, I need to multiply first, so x by y, and then sum it up. I swear to you, the vast majority of times people get a math mistake on the Pearson's R, it's because they did this backwards. And they multiplied sum of x by sum of y. No, multiplication first. Right, then on down to these pieces here. So sigma x squared. Same issue here. Okay, you've got an exponent and you've got a sum. You need to do exponents first. So in order to complete this piece, you need to square every value of x and then sum up all those squared values. Okay, you don't just square the sum of y, because you need to use the exponent before you sum. So square all of the x values and then sum them up. Likewise with y, square all of the y values and then sum. Okay? Once you have those 5 pieces, sum of x, sum of y, sum of xy, sum of x squared, sum of y squared, you plug your pieces into this formula and you solve it down. From there, it's nothing too crazy. You've got some brackets indicating that you need to do everything within the brackets first. Other than that, you just sort of solve and simplify bit by bit. So, like I said, I'm going to show you an example of completing this work, and then there's a practice problem for you to try right away. Because again, it might look advanced from the outset, but nothing is outside of the realm of your capability here. So here's my example. Let's say I'm interested in the relationship between hours of sleep a student gets in the 5 days before an exam and their score on that exam. I'm going to pull 10 people. I'm going to get their sleep score and their exam score. Your data would look like this, right? You've got your 10 participants, you've got their sleep score, variable X, and their exam score, variable Y. Again, the correlation is about evaluating pairs of raw scores, so I don't need to standardize anything. It doesn't matter that sleep and exam score are on different quantitative scales. That's okay. All I need to do is make sure that all of these scores are paired together. So for this first participant, that is their sleep score and that is their exam score. Likewise for participant 2, that's their pair of scores. This is what the data is going to look like when you are ready to do your correlational computation. So, in evaluating whether or not there's a relationship between sleep and exam score, these are those 5 pieces I referenced needing. Sum of x, sum of y, sum of xy, sum of x squared, sum of y squared. Just computing these pieces is going to take up the vast majority of the time when you're running this hand computation. So the most work you do is at this step before you even get to the equation. So to get this table of scores, I would recommend setting your work up to look a little bit something like this. Okay, you've got your variable x, you've got your variable y. Just expand on that little table to have an xy column, an x squared column, and a y squared column. Then from here, you can kind of decide what you want to do first, but you just go through and you complete this table. So you can complete that xy column first, which every value in that column is just the x by y or x times y value in that row. So you multiply for every participant their x score by their y score, and you just go on and you do that for all 10 participants. X squared is just every participant's x score multiplied by itself. Okay, so square it, and then do the same thing for the y values. So each value in the y squared column is just that participant's y squared. From there, you just need to sum up the total in each one of these columns one at a time. So sum of x, you just sum up all those x scores, sum up all the y scores. Sum of xy, again, you multiplied x by y first, and then you sum up that column, and that's how you get sum of xy. For x squared, again, it is crucial to square all of the x values first, and then you sum them up. And likewise for sum of y squared. Once you get all of those y scores squared, then you sum them up second. Then you just plug in the pieces into their appropriate spot in the equation. It's always good at this step to make sure you're being careful and just plugging things into their designated spot correctly. So then here's my filled out equation, and then from here I just simplify. I typically simplify in a series of steps. I will basically knock out a series of functions at the same time. So for example, I would do this first, this, and this all in the same step of simplification. You're allowed to spell out your work sort of as much as you want. So once you simplify that equation down, you're left with an R value of negative 0.68. And that's my Pearson's R. So then you have to actually interpret. So is there a correlation between sleep and exam score? There's a couple different ways that you can interpret it. We're not going to get into significance testing just yet. The ways that you can interpret your Pearson's R before you actually slap a p-value on it is you can just eyeball it using the rule of thumb method. You can use these sort of quick and dirty cutoffs for what is considered weak, medium versus strong correlation. I would say in general, you should steer clear of the rule of thumb method. It doesn't take into account things like the sample size. So it definitely is not going to be the most accurate representation of just how strong your correlation is because it sort of just uses the R itself without taking any other information into account. But this is one method that exists if you don't have your significance testing going yet. As I mentioned earlier, correlations are all about variance shared between variables. Essentially, if two variables are correlated, they vary together. In other words, correlation is about capturing the amount of covariance that variables share. So the variables, if they're correlated, sort of change together. Additionally, the correlational value itself describes the amount of variability shared between your variables. This is sort of why the Pearson's R works the way that it does and why you don't need to standardize your variables before analyzing. It's because the Pearson's R is, in mathematical terms, capturing the amount of covariance that your variables share. So, an interesting mathematical uh, implication of the fact that correlation is about variance shared is that you can very easily transform your Pearson's R into a value that indicates percentage of variance shared with what we call the coefficient of determination, which is notated as R squared. And if you're thinking that sounds pretty easy, is it literally just squaring your Pearson's R? Yes. Literally, to create your coefficient of determination, you just square your R value. So in our example, we squared our Pearson's R. This puts your correlation, again, into terms of percentage of variance shared. So another way that you could interpret this relationship between sleep and test scores is that 46.2% of the variance in test scores was accounted for or was associated with the variance in sleep. Given the range of a Pearson's R can only be from -1 to +1, this means that your coefficient of determination can only range from 0% to 100%. This means that there is a big chunk of variance left out there in test scores that would be due to factors outside of sleep, and that's okay. We can have a significant correlation even if the variance explained between variables is not massive. The idea is this is an appreciable amount of variance such that we know that sleep has something to do with test scores, even if there's other factors that go into the ultimate test score that you get. So then, of course, I always need to harp on the important points. Does this particular hypothetical example demonstrate that getting less sleep caused exam scores to increase? No, of course not. You want to make sure that you do not make that leap to causal claims on the strength of correlational research. What correlations imply is that variables are associated. When variables are associated, this could mean multiple things. It could mean that one variable causes change to the other or vice versa. You never know when you're doing a correlation whether or not your x caused changes to your y or y caused changes to x. Now, sometimes you have sort of logical reason to be able to rule out one of those directions. For example, in this hypothetical, the sleep happened in the days preceding exam scores. So you do know that because of the way the sequence of time works, that exam scores can't cause sleep to change because we don't have a time machine. So we can at least rule out that exam scores caused sleep to change. Now, even though you ruled that out, you still can't necessarily claim that sleep caused changes to the exam scores. And the reason is that correlational research does not let you rule out a possible third variable causing changes to both x and y. For this example, let's say anxiety was associated with both sleep and exam scores. And so sleep wasn't directly causing changes to exam scores, but it was the anxiety associated with changes to sleep that more directly caused changes to exam scores. So whenever you have correlational analysis, think about which variable likely causes the other if you can rule out either of the directions, but always keep in mind that a correlational analysis will not be able to rule out some other third variable that was pulling the strings of both x and y. So then here's your practice problem. I'm just going to walk you through the steps. I encourage you to pause this video when I put the data up on the screen. Give yourself about 10 minutes and just test yourself. See if you can do a correlational analysis. If you get anything wrong, come back and catch where it is you went wrong so that you know how you could go right in the future. So in this practice problem, let's say I'm interested in the extent to which nostalgia is associated with happiness. Nostalgia, again, a favorite variable of mine. So let's say I ask 10 students a series of questions about their level of nostalgia and a series of questions about their happiness. This is going to yield me an average nostalgia score, a single nostalgia score for each participant, as well as a single happiness score. So my data would look like this. All 10 of my participants have their nostalgia score and their happiness score. Okay, so to complete this problem, again, I would recommend 10, 15, maybe minutes is the average that I would say typically takes to run a Pearson's R. But I would recommend just pausing this video and working through your computation of the Pearson's R. Keep in mind that it necessarily will be between the range of -1 to +1. So go ahead, pause this video, and come back and restart when you have your Pearson's R computed, and we can talk about it. All right, so now I want to walk you through the steps of computing your Pearson's R. If you followed along this video, you'd know that the way I would recommend structuring your work is to create a table to help you compute all the pieces you need. So you create this table where you've got your column for all your x values, column for your y values, xy column, x squared column, y squared column. Okay, now the process is just going to have me filling out this table bit by bit. So maybe you start with the xy column, maybe the x squared column, y squared column. Then from there, you need to sum up the total for each column one at a time. So you got your sum of x, sum of y, sum of xy, sum of x squared, sum of y squared. Again, if you inadvertently multiplied this value by this value to get this value, you'll notice that you were off pretty substantially. This is obviously going to completely throw your correlational analysis, so make sure that you're doing the steps in their proper order. So then from there, you use the equation and you plug in all the pieces that you need. Again, my preference for simplifying down an equation like this is to take out a few steps at a time. So my first round of simplification, I would do this 53.25 by 69, square this value, and knock all three of those pieces out at once. But it's really up to you as long as you're following the order of operations. Don't neglect that there's a square root there on the denominator. I ended up with a Pearson's R of 0.78. Did you get it right? Hoping you did. So this indicates a strong positive relationship between nostalgia and happiness, whereby more nostalgia is associated with more happiness. Reflecting on cherished memories of the past, as we know from nostalgia research, is associated with a host of psychological and well-being benefits. So now I'm just going to show you real quick how you could check your work in SPSS, and we'll be doing a lab quiz to do some correlational analysis. It's pretty easy to do. You just go to Analyze, Correlate, Bivariate. Bivariate just means two variables. So this is a bivariate correlation. And then you select the variables that you want to analyze the correlation between, and you click them over into the right-hand side. You don't need to change any other settings. You keep that Pearson correlation coefficient selected. You can flip back and forth from two-tailed to one-tailed, but you can just keep it on two-tailed if you want, then flag significant correlations. One thing I'll note at this point is that just because this says bivariate correlation doesn't mean you can't throw more than two variables in here at the same time. We're going to discuss in the next round of lectures what we call a correlational matrix. But when you put variables into this right-hand box, essentially what you're going to get is a graphic that shows you all of the combinations of variables. So you don't need to do two at a time. You can throw all your variables into this one correlation and you're going to get a series of bivariate correlations. But here's what this analysis yields. You've got your correlation matrix here. This is your Pearson's R, confirming that we did the work correctly. And it additionally has flagged my correlation as significant, and it's provided me a p-value. Now this is what we're going to start off talking about in the next video. Essentially, this p-value gives you extra additional information. It helps you evaluate for significance, but the p-value itself does mean something specific. So we're going to go beyond just eyeballing our Pearson's R, and we're actually going to subject it to some significance testing. That's basically how you compute your Pearson's R. I hope you got it right, but if not, you're going to have plenty of time to practice. But that's going to end this video for now, so I hope you're doing well, and I'll talk to you soon.